Good morning. We are going to review homework number 5. That's going to cover polarity and bonding and the rest of this chapter. On Monday, a quiz will be sent out for you to take, and knowing the contents of this homework is going to be an important part. So hopefully the video lecture was helpful, as well as the notes, and you've been studying. But to get started, we first want to know, what is a polar bond? A polar bond is simply when you have unequally shared electrons. So shared electrons are not shared equally. Where if it's a normal covalent bond, we would say they are shared. Or nonpolar, again, it means the electrons are evenly distributed across a bond. But if it's polar, one end is pulling more on the shared electrons more than the other. So how do we tell if a bond is polar? We look at the difference in electronegativity. So we do need to know this trend that electronegativity increases up and to the right, where fluorine being the highest. So as you go to the right, as you go up, it gets greater. Now, we're not looking for the total electronegativity between two atoms. We're looking for the difference. So between hydrogen and fluorine, there's a very big difference in electronegativity, so it's very polar. But hydrogen and iodide, if you were to look up their values, 2.5, 2.1, a difference of 0.4, it's fairly we'd call nonpolar. So nonpolar is when they have very similar electronegativity. So it means they pull to very similar extents. Again, if it's anytime it's bonded to itself, it's nonpolar. Or if the value is really small, like carbon and hydrogen, I want you to know this example because it's very common. That difference of only 0.4, we would say it is nonpolar. So we can use this difference in electronegativity to tell whether a bond is likely to be polar, nonpolar, or ionic. So first we have carbon and hydrogen. Now, if I didn't say it before, it doesn't really matter whether there's 4 hydrogens or 2, so you can ignore the subscripts. But if you were to look at carbon having a value of 2.5 and hydrogen being 2.1, that difference of 0.4, we said that would qualify as nonpolar covalent. So that means between carbon and hydrogen, the bonds are shared pretty much equally. Now, zirconium and oxygen. Now, I would hope from last semester you could already say, well, if this is a metal and that's a nonmetal, then this is ionic. So we can confirm that by looking up that zirconium is 1.4, oxygen is 3.5, so making a difference of 2.1. So since that falls greater than this 1.7, we would classify zirconium oxide as ionic. Again, you would have already expected that, but this just gives this whole idea that we can classify it by the difference makes it a little more quantitative. NH3. So we have nitrogen is 3, hydrogen is 2.1. That is a difference of 0.9. So that falls in the middle of nonpolar and ionic. That is polar covalent. So this is a polar bond. Copper fluoride. Now, here you have a metal and a nonmetal, and your first thought would be ionic. And so when we go and look up copper, it's 1.9. Fluorine is 4. So the difference is 2.1. So again, that fits that expectation that it would be ionic. Now, the only time you don't really have to know the exact values, besides carbon, hydrogen, to know it's nonpolar, is if it's bonded to itself. There's no way if it's bonded to itself, it can be polar. Nope, that's not spelled right. So since they have to have the same electronegativity, it has to be nonpolar. So you won't generally have to have this table for electronegativity. I want you to just know the trend. So generally, the further apart the elements are, the more polar they're going to be. And the closer they are, being if they're the exact same element, the lower the polarity. So if we wanted to go from highest polarity to lowest, we can very quickly say, well, the lowest is going to be when it's bonded to itself. And then looking at carbon and oxygen and carbon and selenium, so it's carbon with these two, we see that oxygen has the higher electronegativities than selenium. So the difference between those two is greater between carbon oxygen versus carbon and selenium. So carbon oxygen would be the most polar, and that would be carbon selenium bonds would be in the middle. I want that to middle. Similar question here, highest to lowest polarity. Now, they all have fluorine. So again, the one furthest away from fluorine would make for the most polar bond. So we have bromine, chlorine, and astatine. Oh, sorry, that's arsenic. So chlorine, bromine, and arsenic. So the two that are closest are fluorine and chlorine. So they have only a difference of one. And because they're the closest, they're going to be the least polar bond. The next two, fluorine and bromine, they have a difference of 1.2. So that's the next biggest difference. And so it's the next most polar. But then the most polar is fluorine to arsenic. It has a difference of 2. So again, the greater the difference in polarity, or the electronegativity, the greater the polarity. So generally, the further apart the elements are on the periodic table, the more polar it's going to be. So typically, you're not going to find just single bonds in a molecule. Like, I mean, these couple of these are, but generally you'll have a molecule where we have to look at how multiple bonds together determine polarity. So all of the different bonds determine the bond dipole moment, where it's just the quantitative measurement of how polar it is. This is experimentally determined, and the greater the value, the more polar it is. So what we need to look for pretty much is symmetry. So here on this first one, we have 4 bonds. Now, we've already said if you have carbon-hydrogen bonds, these two, they are non-polar. So they are not a contributing factor here. However, chlorine is more electronegative than carbon. So having this thing pull electrons towards chlorine away from carbon, there's a polar bond. Now, there's also one over here. Now, because there's only 2, most of the electron density is pulled to this half of the molecule, and that is going to make this thing polar. Now, here we have boron triiodide, and these bonds are not very polar. The difference between boron and iodine is only 0.5. So, but if we either way, if we do go ahead and say they're polar, even though they're just slightly polar, we would still say that because it's completely symmetric, if electrons are pulled to this iodine and that iodine and that iodine, because it's trigonal planar, and these bonds are completely symmetric, all of the polar bonds cancel out, making it completely nonpolar. So to be polar, there needs to be dipole moments just pulling to one half of the molecule, not being pulled to all different sides. Here we have 1,1,1-difluoroethylene, and there's 2 dipole moments. So if we were drawing the arrows, we would draw the arrow from carbon to fluorine this way and a carbon to fluorine that way. So all the electron density is being pulled greater to this half, not on this half. So because of that asymmetry, this thing is polar. Between oxygen and sulfur, again, oxygen is more electronegative. And so if this thing was linear, if it was straight, then it would be nonpolar. But because of this non-bonding pair, instead of linear, it's bent. Again, that's Vesper theory. And so now these 2 polar bonds, they don't perfectly cancel. More electron density is pulled to this half of the molecule away from this half. So it is polar. Now, in this last one, it's carbon with 4 bonds, similar to this first one. But instead of having 2, it has 4. And you might expect, well, with more polar bonds, certainly it's more polar, but it's exactly the opposite. Having more polar bonds pulls electrons in different directions, and the more electrons are distributed, the less polar it's going to be. So since this thing's completely symmetric with 4 polar bonds, it is completely nonpolar. What did I do there? Undo. There we go. So this one's, again, very similar, just more examples. Would be classified as polar or nonpolar. So first, if there are no polar bonds, then it can't be polar. So anything bonded to itself has the same electronegativity, so the difference is 0. It's nonpolar. Here we have, this is what's called phenol. It's a chemical, if you've ever used a sore throat spray, then this phenol is it has a, oh, I can't remember the word, a numbing effect. That's not the fancy word, but phenol is the active ingredient. So remember, each corner here is a carbon with a hydrogen, and those are all nonpolar. But oxygen is notably more electronegative, so it's going to pull electrons towards itself, making this thing polar. Here is acetone, a nail polish remover. Again, oxygen is more electronegative than carbon, so electrons are pulled to this half, this top part of the molecule, away from the bottom half. So we would say this top has a partial negative and this bottom has a partial positive. So this thing is, oh, not there, not there. This thing is polar. Nope, nope, nope. Polar. Here we have hexane. So 6 carbons, 14 hydrogens. None of those bonds are polar, so this thing is non-polar. Lastly, we have hydrogen cyanide. Nitrogen is more electronegative than carbon, so there is electron density pulled to this half of the molecule. This bond is non-polar, so altogether we say this thing is a polar molecule. The last few questions deal with sigma and pi, and again, hopefully you looked over the notes about the differences between sigma and pi bonds. The main thing being, if it's sigma, or if it's only a single bond, then there's a freedom of rotation. In the notes that I showed in the video, this thing can rotate around and around and around. So these two molecules here are actually identical. It doesn't matter whether you put the fluorine the bottom or the top or on the right, because these can freely rotate, and so there's not a distinction between the two. So with sigma, electrons are shared directly in between, and it allows for that rotation. Again, with pi bonds, when you have a double bond, the second bond is bonded above and below. And the consequence of that is it locks them into a certain configuration. So up here, these two chemicals are different. They are distinct isomers from one another. This is the cis isomer, this is the trans. So it doesn't have that same freedom of rotation when there is a pi bond, because there's electron density above and below. So we would say sigma bonds overlap electrons directly between atoms, while pi bonds overlap above and below the plane between atoms. And then the other big thing I want you to know is sigma bonds allow for rotation, while pi bonds do not. So again, looking at how many sigma and pi bonds, here we have, this is dichloromethane. There are 4 single bonds, which means there are 4 sigma bonds and 0 pi bonds. Here we have that 1,2,1,1 difluoroethylene. There is 1, 2, 3, 4, 5 sigma and that double bond has 1 sigma as well as 1 pi bond. Here we have something, I don't want to bother looking up the name, but every bond has 1 sigma. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I probably should have mentioned this, but this is a shorthand notation for 3 single bonds to hydrogen. So carbon, hydrogen here, carbon, hydrogen there. Oh, don't move that. Carbon, hydrogen everywhere. So this is 3 separate bonds. So again, that's 3, 4, 5, 6, 7, 8, 9, 10. And then every double bond is 1 pi, and every triple bond is 2 pi. So in total, there's 3. So this question again is trying to get you to think about the sigma versus pi, and which pair of these are isomers and which are the same drawn differently. So for this first set, they are different. So double bonds make different isomers. So there is no rotation. So whether they're both shown on top or bottom, they are different. But then if there are only single bonds are the same molecule, not isomers. So these are just drawn differently, but the fluorine, whether it's up here or down here, it can rotate around, and so these are exactly the same thing. So these are not isomers, these are the same, these two are different isomers. And then finally, again, there were several slides on plastics, polymers. So again, please look over what polymers are. You don't have to know in detail these polymerization reactions, but again, the general idea is they keep linking one to another, to another, to another, to another, to another for thousands, hundreds of thousands to generate polymers. And there's a number of different ways to change what type of plastic or polymer it is. The biggest one is changing the monomer. So whether it's propylene where there's a carbon, or chlorine for chloroethylene, or fluorine for Teflon, so if you change the monomer, you change the properties. And there's, again, a bunch of different stuff I've already talked about in another video. So what are plastics? They are polymers of repeating repeating small molecules. How do you get different ones? Change the identity or properties of the monomer. Again, it could be a copolymer. Guess it did mean that. It could be a copolymer where you use more than one type of monomer. Like in Legos, you have ABS, where you have these 3 different. But either way, there's a lot to polymerization. Again, there's natural polymers like proteins and DNA and other stuff. But that's pretty much it for the homework. Definitely, please email me if you have questions. I'm happy to answer whatever. Again, on Monday, I'm going to send out a quiz for you to take. So please set aside, make sure you have 1 good hour of internet connection, have a periodic table handy, and yeah, be ready for that quiz. On Wednesday, I'll be sending out a test. So again, be prepared for that. I hope you have a fantastic day.